Hi, in this lecture I'm going to talk about the notion of intensity. So waves carry energy. For the most part so far we haven't really talked about that too much, but it's obvious that they do carry energy, and you can probably guess, based on what you know about oscillators, that the energy they carry is going to be proportional to the amplitude of the wave squared. Now the exact expression depends on what type of wave it is. Right? We're not going to go through all different examples, say. But here's what's going to happen in general. If you've got a wave that travels in a 1D medium, like a string, right? A wave traveling along a string, you shake your hand here to create a pulse that travels along the string. Well, all that energy that's in that pulse just goes from one end to the other. Now, realistically, there's damping, right? There's air resistance, there's internal forces in the string, the different friction between different fibers of the string, or whatever it is, right, that makes up the system. There's usually, realistically, going to be some damping, so not all the energy gets there. But if we ignore that, or if that's small, then we can say the energy produced here is going to get there. Now let's compare that to, say, light waves, or sound, but here I'm going to go with light. Imagine I've got a light source here, a candle. So light's going to spread out, right? And I've drawn it in 2D on a sheet of paper, but of course you could imagine spreading out in 3D in sort of spheres, right? So it's like a small sphere and a bigger sphere around it, and those would be the wave fronts. They're spherical. So if this is a wave crest, it's also coming towards us and going backwards, and so on. So the light goes in all directions. So that means the energy that gets produced here spreads out, right, in those spheres. Let's suppose this candle produces a certain amount of energy per second. Right. Then I ask, well, what if I have a little sort of window here in which I'm catching energy, little area A. I can't really draw it, it's meant to sort of face the candle. I can ask, well, how much of that energy goes through the little window? What power do I receive here? Power, remember, is energy per time. Well, here's how I might calculate it. The power received on area A, and we're going to assume area A faces the candle. It's going to be equal to the power produced by the candle times the fraction that this area makes of the sphere that is the size, essentially the spherical shell that includes this area, right? So if the area is 30 centimeters from the candle, then what fraction of the 30 centimeter big sphere is made up by that area? So times A divided by, what's the area of a sphere? It's 4 pi r squared. Another way to think about this is that it's essentially we're counting the flux, the energy flux. How much energy is going through this area? We've met flux before in other contexts, and maybe that makes sense to you. So let's say this again. I have this thing here, the candle produces energy, and maybe I can track like the energy produced in like between now and now, right? Of course, you make those intervals much shorter, and you're going to imagine there's this here, and then there's another little ring behind it, and I'm asking what's the energy within that thin sort of shell that spreads out, right? Well, the fraction of that total energy that gets that little window here is the area of the window divided by the area of the shell when it reaches the window. That's where the 4 pi r squared comes from. R being, of course, this distance here. Right, now if you understand that, visualize it in 3D, then you can use intensity. Right, this is kind of the main insight here. Intensity is the power received per meter squared. So I can say this is power produced divided by 4 pi r squared times A, just rearranging it, because then this quantity here is called the intensity I. Intensity I, in most general terms, that's the power per area. Right, so how many watts per meter squared? How many joules per second per meter squared? I mean, always visualize it as, imagine this is not a candle, but it's the sun. Put a solar panel here. How much energy, how much power are you going to receive in your solar panel? Well, it depends on how intense the light is, which depends on how bright is the sun, how far are you away from the sun, and then, of course, the area of the solar panel itself. Let's work with that. Let's work an example. So the example I want to do is I want to calculate the power output of the sun. Example. Calculate the power output of the sun. Right, so how we can do that? The information we're given is the following. The intensity on Earth, due to sunlight of course, is about 1360 watts per meter squared. What does that mean? You put 1 square meter of solar panel down on the ground so that the sun shines straight onto it, right, not at some angle. And then it's going to receive 1360 watts. Right, so that means joules per second if it's 1 square meter in size. That's something you can measure. The other information we need is how far are we away from the sun. So distance from sun r is equal to about 1.5 times 10 to the 8 kilometers. Let's switch to meters because meters squared, so 10 to the 11 meters, 150 million kilometers. Right, that is the distance of the Earth from the sun. Let's find the power output of the sun. We're going to use this expression here. Intensity is power produced divided by 4 pi r squared. We're going to find the power produced. So we're going to say the power produced by the sun is 1360 watts per meter squared. Multiplied by 4 pi times r squared times 1.5 times 10 to the 11 meters, and that whole thing gets squared. Right, what am I using here? I'm using the fact that the power produced is the intensity times 4 pi r squared. Right, this is what this is. Again, let's visualize it. Here's the sun. And I have, I'm saying, okay, 1 square meter over here, so 1 meter by 1 meter, that receives 1360 watts. Right, that's the statement. That is what we mean by intensity. I've got a meter by a meter. What wattage do we get based on the energy that's contained in the radiation here, in those waves? And then we multiply it, in a sense, by the number of little panels like that that we need to cover the sun at that distance. Right, so we multiply it by the area, 4 pi r squared, so I did here. We work this out. We're going to get, so you multiply those, power produced by sun. And the answer you're going to get if you multiply those is, unless I am mistaken, it's about 3.845 times 10 to the 26 watts. Oops, you can't see this. There you go. Like it's an unimaginably large amount of energy. Another thing to call that would be 3. I mean, you can work it out, right? So it'd be 3.845 times, I guess, 10 to the 17 gigawatts. Or then there are terawatts, petawatts, and so exawatts. You know, you can express in some absurdly large amount of energy. Not sure if that's useful though. Alright, so that's one application of intensity. Now let's imagine we want to put up a solar panel, we want to put it out into space, we're going to put it on Mercury, because Mercury is close to the Sun. Right? So what do we do then? How much energy how much power does get produced by a solar panel on Mercury? Power received by a solar panel on Mercury. Okay, so how big is our solar panel? Say it has an area of 20 meters squared. Right, it's a very chunky solar panel, maybe the size you find on a rooftop. How far is Mercury from the Sun? We can go look it up. It is about, Mercury is about 3.6 times 10 to the 10 meters. So it's 36 million kilometers, whereas the Earth is 150 million kilometers, so it's a little bit more than 20% of this. Like, it's a lot closer than Earth, right? It's a bit more than a fifth of the distance. So how do I find the power received? So one thing I could do, I could say, well, the power received, right, like this, is the power produced, which we worked out, times the area of the panel times area of our panel divided by 4 pi rm squared. We'll plug in the values, you worked out this, we can do this, right? But there's also a shortcut. The shortcut is that if I know the power that is received on Earth, or the intensity on Earth, I can find the intensity somewhere else by just working with the ratios of the radii. So, or we could do it the following way. Imagine we hadn't found the power output of the Sun. Maybe we never cared about it. So just observe the following. I, Earth, right, is equal to the power of the Sun, thing we worked out, the power produced. I guess I should be consistent here. Call it the power produced, divided by 4 pi r Earth squared. R Earth, 150 million kilometers. Meanwhile, the intensity on Mercury is the same power produced, because again it's the Sun, divided by 4 pi r, the distance of Mercury squared. But that means I can just find one from the other without intermediate step. So for example, what I could do, could say the intensity on Mercury is the intensity on Earth multiplied by the radius of Earth squared divided by, not of Earth, of Earth's orbit squared, divided by the radius of Mercury's orbit squared. Right, so I'm sort of taking this expression and I'm multiplying it by RE squared to get rid of this, and then I'm dividing it by this to change from that to that expression. Right? So that means I never have to figure out what the power produced is. I can just work with those ratios. So this is 1,360, and now so this was 150 million kilometers. And that gets squared divided by 36 million kilometers squared. Notice I can just work in millions of kilometers here because it's the same unit. Any factor is going to cancel out. Right? And so I can work it out that way, and I will find that it is 23,600 watts. That's the intensity. Now if I want to find the total power received from a solar panel, I just multiply this value by the area of the solar panel. So power received is going to be the intensity of mercury. It's the power per square meter. Well, how many square meters do I have? 20 square meters. So that comes to 4.72 times 10 to the 5 watts. Of course, I should have put this, of course, watts per meter squared. Excuse me, right? Power per area. So you can see intensity here is a lot bigger than Earth, right? So Mercury, great place for solar panels. Problem is how to get the energy home. Well, that's different questions that we leave for others to figure out. Okay, now, in a sense, that's all there is to it, right? The rest is just more application, more examples. There's one more thing though to mention, just so you've seen it, and that is that sometimes intensity is measured on a log scale. It's measured on a log scale for convenience. And part of it is that our perception, say, of sound or of light is logarithmic, right? So when you say, oh, this is twice as bright as the other thing, whatever it exactly means, it's probably, a multiple, like brighter by some factor. So like something that's, if A is 10 times as bright as B and B is 10 times as bright as C in terms of intensity, A doesn't seem 100 times as bright as C to us. Right? Our eyes work on a sort of logarithmic scale, our ears do too. So, for example, there's the decibel scale for sound to measure intensity, and that is the number of decibels, and that's what you might hear when you read about noise pollution or something like that, right? You come across that measure in decibels. The sound intensity measured on the decibel scale, it's given by 10 times the log to the base 10 of the intensity divided by 1 times 10 to the minus 12 watts per meter squared. By that many decibels. Now this is just an arbitrary number. It's somebody at one point or another decided that 1 decibel is defined in this way. Now you could have picked a different number that would just change the scale in a sense, right? So, but this is just, don't ask why, it just works. The reason we pick this number as opposed to other numbers is because then the sort of numbers from 1 to 100 correspond to the loudness of sound that we receive day to day. Right, so 0 decibels is kind of the lower end of what we might be able to hear. So 10, 20 decibels, it's a whisper. 80 decibels is a loud machine. Anything above 120 is going to be really painful to the ears. So this is sort of the lower level, a kind of a lower limit of what our ears can pick up. Of course, the higher the intensity, the more energy per second, the louder it seems to us, right? So it's just a convenient way to put those giant powers of 10 into the numbers 1 to 100. Right? That is what this does. Similarly, in astronomy, people talk of magnitudes, of apparent or absolute magnitudes for light, and then the magnitude m, essentially the brightness, is sort of defined in a similar way, except to make things even more confusing, you put a minus sign in front, and then it's log 10 I over some reference intensity. Again, that depends on, are you comparing to stars, what frequency, what part of the spectrum are you looking at, visible light or ultraviolet or infrared. So there's some value much like this one that you might pick here. But the minus sign means that lower numbers actually means brighter. So for example, the sun is equal to has a brightness about -27, which is really, really bright, and then sort of the brightness of a barely visible star is maybe something like +5. So it's a really counterintuitive scale to use, but if you're interested in astronomy, you're probably going to end up using it to characterize the brightness of stars, either the apparent brightness, how bright does it seem to us, or the actual brightness, like how much power does a star emit. Either way, the concept of magnitude comes in. This one, though, decibels, is definitely something you'll come across in daily life. Here or there, you buy a vacuum cleaner, it might tell you how many decibels it has. Of course, it depends on how far away you are, right? But this is how you would calculate it, or how you conversely convert decibel number back into an intensity. But really, this is just plugging in numbers. The key about intensity, the key to take away from all of this, is this R² dependence, right? Because it spreads out in this sphere, the power that you receive gets reduced by a factor of R² the further you go away. So if you go twice as far away, the power received is a quarter of what it was before. That's why the outer planets, Neptune, Uranus, they get very little light. The dwarf planets beyond that, Pluto, Eris, all those, very dark. Right? If you're 10 times as far away from Earth, you only get 100th of the energy from the sun, for example. But if you get that, the rest is just application and examples. So thanks for watching. Good luck with all of that.